gentlemen, welcome back from our short break. And thanks to our fellow volunteer host, Folia, for the great speaker interactions. I'm here ready to continue the hosting. Please welcome Christopher Neugebauer, a seasoned software engineer and a devoted member of Python Software Foundation's board. Christopher is here to share his expertise in Python's concurrency tools and how they can help us to solve Wordle puzzles. Without further ado, let's give a warm welcome to Christopher.
Hi, everyone. Before we begin, you may have noticed I have been inconveniently scheduled against the Blue Angels. If you can't hear me, put your hand up and I will try and repeat what I've said. Also, if the noise gets loud, I may stop talking involuntarily. I apologize for that. Hopefully it doesn't happen too much, but that's a thing we just need to be prepared for. I've never presented while an air show has been going on directly overhead, so there's a first time for everything. Thank you all for coming along. I'm here to talk about using Python's built-in concurrency tools to talk about solving Wordle. If you've come here for a detailed discussion of Wordle, you might be in luck. If you're here for a really detailed discussion of concurrency, you might find this talk a bit lacking. Both of them together, very good though. Before I begin, disclaimer, Wordle is a trademark. It's owned by the New York Times. I am not from the New York Times. I am from the Python Software Foundation. I'm the organizer of the North Bay Python Conference. I also work for a company called Maribel Health. If you are interested in any of those three things, come and talk to me. Just don't talk to me about things going on at the New York Times because I'm not from there. Hey, so today I'm going to be talking about Wordle. I'm going to be talking about concurrency, and I'm going to be talking about things that are related either to Wordle or concurrency. Are we clear? Excellent. Hey, so I play Wordle most days. I play it in hard mode. I am comfortably average at this as a human being. I usually take 3 or 4 guesses. One day back in August, I solved it in 2 guesses, 2 days in a row. I was very excited by that. These days, my starting word is the word tears, which I know for a fact is not a possible answer in Wordle, but as you'll see later, it's what my solver thinks is the best starting word, and I wrote that code, so who am I to argue with my own code? Tears is the present tense of the verb to tear, which is the act of balancing a scale. My old starting word, irate, was unfortunately the answer back in July, well after I'd started using tears as my starting word. Oops. Anyway, there's no spoilers in this talk. I wrote most of the slides back in August. Might have looked at WordleBot around then to get some interesting data, but nothing is going to solve today's Wordle. So if that's worrying you, you're good. Also, I think it's also really important to mention this talk won't change how you approach Wordle as a human being, which is great because I would hate to spoil your enjoyment of a thing that I find generally quite pleasant as well. I didn't spoil my enjoyment of Wordle. Now, I don't think Wordle solving as a human being resembles solving Wordle like a computer, which is because we as human beings are not very good at reasoning about a large amount of data in our head. And the space of 5-letter words is actually pretty big. The YWAL word list, which is an open source word list for word games, it's what my solver uses, has 12,000 odd 5-letter words. That's a lot of words to think about. And if you filter out words that are obviously plurals, which is a thing that Wordle does for its answer list, there is still well in excess of 8,000 possible words. It's very hard to reason about that many things in your brain. And even after you make a really good first guess, usually there's somewhere between 60 and 500 words that are left over to guess. And it's really difficult to remember which 60 to 500 words are going to be left over depending on which letters are in your first guess. And so what we do as humans is we just do what everyone else does. And we can thank the New York Times for giving us some details about how people actually play Wordle. They have a site for subscribers called WordleBot, which is a combination Wordle solver and a player statistics site. And if you check in on WordleBot, you get some really interesting information. So here's a screen grab from WordleBot on a morning in Australia. I actually woke up really early to get this screenshot. I woke up at 6 a.m. So you've really only got early risers and people in New Zealand included amongst these stats. That's why it says there's only 1,000 odd solutions. And you can see that most people in Australia and New Zealand solve using adieu as their chosen starting word. And why do we think most people start with adieu as their starting word? It's because it has a lot of vowels in it. And when people started playing Wordle for the first time, it was a word that people really latched onto because it would tell you which vowels were in your word. Now, I live in California now, and I usually play Wordle 17 hours later. And you can see that the most popular word when I took this was least. Adieu is still up there, but now there's a bunch of people in the US who have played, who subscribed to the New York Times game site, and they saw that Wordlebot's preferred starting word was least, and so everyone copies that. These days, Wordlebot has started to use slate as its preferred opening word, and now slate has started to overtake least as the most popular starting word for people in the US. People in Australia and New Zealand still use adieu. So once you get past that opening guess, it's really all just down to remembering a few good second guesses, and then once you get into the game, it's really just down to how much you can reason with the information that's available to you. But everyone's first and second guesses are really just based on pattern matching and guesses. So yeah, we do not have the mental capacity to play Wordle like a computer, and Wordle can play a lot more closely to optimally for a given solution word. So Wordle is a guessing game, and the way to play a guessing game is to make a guess about what word we think will reveal the most information about a solution space. So information, thankfully, is a formal word too, and we can use that concept to figure out how to build a solver for Wordle. So let's look at a different guessing game that's a lot simpler. You've probably played this one, where you have to guess a number between 1 and 1,000, and the game will tell you, an oracle will tell you whether the answer is higher or lower. And you have a solution space, and how do we make our first guess? Hey, we pick the word in the middle, or the number in the middle rather, and immediately you halve the solution space, and you can guess in the middle of that space, and you'll have half the solution space each time. And so you can actually play this game optimally by guessing the number in the middle every single time, and eventually you'll get the solution. Okay? And so back to this idea of information. Every time you halve the solution space, the base 2 log of the size of the solution space reduces by about 1. And the way that we phrase this in information theory is we describe this halving of the solution space as gaining 1 bit of information. And so you can talk about this with a bit of maths. The information gain is the base 2 log of the solution space less the expected base 2 log of the solution space after a guess. And for our guessing space, that expected information is always 1 bit. Okay? So we can apply these theories to Wordle, but the difference is that with Wordle, you can't actually play optimally. The same guess will reveal different information depending on what the actual answer is. So the best thing that you can do is make an estimate. And how good does our estimate need to be? Well, we can see that the size of the solution space is about 14 bits, and we know that we get 6 guesses in the game. So that means if we can really reveal about 2.33 bits of information per guess, we will solve Wordle within our 6 guesses. So here's a worked example from a few weeks ago. I guessed tears as my first guess, like I said I would, and I got a green T and a yellow A. So T is in the right space, A is in the word, but not in the correct space. So if I were to guess the word today, depending on the information that is revealed to me, I might end up with 3 potential answers remaining. I might end up with 1 potential answer remaining. So that's 13 potential answers that get split into 7 groups. And so the expected solution space, which is averaging the number of words in each group, is 1.86 words. And so that would be a gain of 2.81 bits of information. And that's better than the 2.33 that we need. Now, on the other hand, if I guess the word Titan, I would still end up with either 3 words or 1 word, but there are far more ways for just 1 word to remain than there is for 3. So that's 13 words split into 9 groups of possible solutions, which is an expected solution space of 1.44 words, which is an expected information gain of 3.17 bits. So there are different guesses that will reveal different amounts of information. So that gives us a strategy for playing Wordle. The idea is that you'll pick the word with the lowest expected solution space size, guess with that word, eliminate all the words based on the information you get, and repeat until only one word remains in your solution space. So now we can look at some Python code. Here is the main loop of my Wordle solver. Basically, we make a guess, and then we classify the guess we've made against the actual target word. And then we filter the solution space against the classification that we got. And you can see that I've decomposed that down into functions, so you can see where each bit is happening. And so now we can look at the implementation of those functions. So this is the classification routine. I'm using an enum to describe whether a letter is not in the solution or if it's a yellow or green answer. And then the classifier itself is pretty self-explanatory if you play Wordle yourself. Basically, we return a 5-tuple of these classification objects, and because tuples are hashable, we can use those as a key in a dictionary. And you'll see why using those as a key in a dictionary is important in a moment. So this is the implementation of the filter function. It takes those classification tuples, and it will run them against every single word in the solution space, and it will return only the words in the solution space that match the classification. Hi, Blue Angels. I've written this solver 3 times now, and every single time I've used a for else block. Generally, I recommend not using for else blocks, but here it actually results in pretty understandable code as long as you know what a for else block does. So if you're looking for an example of a for else block and where to use it, here's a slide for you. If you didn't want to use a for else block, you'd need to split this into several separate functions. It is much, much neater this way, in my opinion. Exceptions to every rule. So here's the point where we actually make a guess. So here's the first function. We basically loop through the space of possible guesses. We find the guess with the lowest potential score, and then that word with the lowest potential score is our guess. It does not have any tie-break facility, which means it might not always make an ideal guess, and you'll see that this actually impacts behavior when we start adding some concurrency to the code. And then you also need a scoring function, and there's another loop in that. We go through every potential answer. We classify our guesses if the potential answer is the actual answer. Can you still hear me over that? Okay, cool, I'll keep talking. And then we'll see how the guess word would split the solution space. The more groups you have, the smaller the solution space is likely to be after that guess. So does this work well? So I'm using the target word snake, and you can see that it solves the Wordle in easy mode in 4 guesses. The word spall here, the second guess, that means to splinter or to chip. So before I move on, there's one code simplification that I suggest using, which is in our make guess function. That's a lot of Python code there. Python code is slow. It can be rewritten like this, which has the nice effect of running the outer loop in some C code, which makes things somewhat faster. So yeah, we can solve Wordle in about 3 minutes on my M1 MacBook, this one here. Let's see if we can do better in Python. So the first place you might start looking is with thread pools. Threads are chains of execution that exist within the same process segment on your system. So here's our make guess function, and again, we have this loop which we do exactly the same thing without modifying any data structures, and the inside that loop is also quite resource intensive. There's that loop again. So this is where the concurrent futures library comes in. It's usually my first port of call for doing any sort of async programming. Much more so than async await, and much, much more so than directly using the threading library in Python. So concurrent futures, you can basically think in terms of calling functions and waiting for a result, rather than working with things like locks, which tend to be quite tedious to work with. And so here's what our make guess function looks like with a thread pool. We submit every potential guess to the thread pool, which returns a thing called a future. A future is an object that will eventually hold the result of some sort of guess. And we're going to associate that future with the word that we use to submit it, so that we can actually remember what that best guess was when it comes back. And you can see we're still using the min built-in, like I use in that optimized looping code. So basically, we just grab each result as it gets completed, and we do that by using the asCompleted function from the futures module. And so we can set up a thread pool with 8 workers. It makes sense to create a thread pool with 8 workers because my laptop has 8 cores. We cannot speed up beyond the number of cores you have in a given machine within reason. And we can go from our looping code, which takes 185 seconds to make its first guess. Vehme, by the way, a Westphalian vigilante society. So we can go to threaded code, which takes 181 seconds to make a guess. So this is where I point out that CPython has a thing called the global interpreter lock, or the GIL, which is a structure that prevents multiple threads from having access to any piece of state that the interpreter holds. In practice, this means that only one Python thread can execute at once. It's worth noting that the GIL prevents concurrency, but the GIL is very, very, very efficient at preventing concurrency. We actually get no slowdown from the various things having to acquire and release the GIL here. They run in basically the same amount of time, even though there's a lock being acquired and released. So the GIL, very, very fast. It's a good thing to know. So are threads useful? Yes, if you have some parallel code that is not run in Python, if you have a C library that you want to run concurrently, if your parallel code is I/O bound, I/O functions in Python release the GIL. If you can run your code on the PyPy interpreter instead of CPython, it's not good for a CPU-bound thing like the Wordle solver that we're trying to write. So our second port of call is the idea of a process pool. So processes are spaces of execution that are managed by your operating system, and they have their own memory. And in practice, it's only possible to communicate between processes over things like sockets or files that are managed externally by your operating system. Now, the good news about processes is that the GIL is a per process thing. If you have multiple processes, you have one GIL per process. And that means that we should see some speed up. And so the only difference between using threads and processes in this case is when you're using concurrent futures, you say that you want a process pool executor instead of a thread pool executor. So it's really like just a small change in one line of code here. And to remind you that single-threaded code took 183 seconds to make a guess. With process pool executor, it took 38 seconds, which is a 4.8 times speed up. So what if we want to see if we can get more speed up now? Well, we can change this max workers parameter from 8 to 16, and our 38 seconds under 8 workers turns into 40 seconds with 16 workers. So my laptop only has 8 cores, so that's obviously the maximum amount of speed up I can get. 16 processors can't run on 8 cores all at once. So you might be wondering why there's actually a slowdown when you go from 8 to 16. And this is because to get a task from one process to another, you need to explicitly communicate across a process boundary, and that takes time. The more you do that, which you get by increasing the number of processes running at the same time, the more inter-process communication there is. So processes work best when you have long-running tasks that don't need to communicate very often. And this actually gives us a bit of insight to run things a bit faster. Instead of submitting thousands of relatively small tasks into our process pool, we can manually split up our problem space into as many chunks as we have cores, and then solve the problem locally within each chunk of the problem space, and then find the global solution across those 8 mini solutions that we produced. So we're making use of that make guess with loop function that we wrote earlier, and we're only doing 16 pieces of inter-process communication rather than the 24,000 pieces of inter-process communication that we were doing earlier. And so here's our version without chunking up the inputs, 40 seconds to come up with our first guess. The version with chunked tasks, you'll notice the opening word is different. That's because our tie-breaking behavior is slightly less deterministic. It solves it in 4 seconds quicker. It is faster by a noticeable margin, okay? Spalt, by the way, means brittle. So processes. Processes are good if you have a small number of large but CPU-bound tasks. It is a lot more work to make process pools work efficiently compared with using threads in, say, Java. It is quite good for writing a Wordle solver. There's a third tool for concurrency in Python, which is using async and await. These are not really relevant to solving something that's CPU-bound. Benji will probably disagree with me to a certain extent, given that we've made that work with pants, but the things that come out of the box in Python, not so good, won't really give us any speed up, and you have to write a lot more code to make it work as well. So finally, we're going to talk about no GIL. Python, as I mentioned earlier, has always had a GIL, and people have always wanted the GIL to go away, because that would enable threading, and threading is much faster, and you have to think less than you do about when you're working with a process pool. So there's a new effort called no GIL, which is making the best effort we've seen so far at removing the GIL from Python and making it usable. You can install no GIL if you have PyEnv on your machine, or you can install it from source. Important to note here, all the previous demos that I've done are with Python 3.11, which is a version which introduced the results of the fastest CPython project. That makes CPython faster. It was not there in Python 3.9, which means that some of the things are going to behave intrinsically smaller. So I figured I'd try out the Wordle solver with no GIL. It takes 40 seconds longer to run in single-threaded mode than our 3.11 version did. So if you've got code running on Python 3.9 and you want it to be faster, just upgrade to Python 3.11, you will get a performance benefit. What does take even longer is if you run in no GIL with a thread pool executor. Instead of taking about the same amount of time as a single-threaded version, the multi-threaded version takes 1.6 times as long. As I mentioned, the GIL is very, very, very efficient at preventing concurrency. There's not really any slowdown from acquiring and releasing the GIL. On the other hand, once you start adding this thread safety, things do start to slow down a bit. There are some demos with no GIL that run significantly faster with threading involved. This is not one of them. So you might ask whether or not no GIL is worth it or not. So firstly, 1.6 times slowdown is a huge improvement on previous versions of the GIL removal. There's been projects for removing the GIL for as long as Python has been around. The authors actually see a way of improving this. And finally, there is a PEP to remove the GIL. It has been conditionally approved. There's a guarantee of sponsorship from a certain large tech company to sponsor the work to make this happen. Signs are that it will land in the next few years, which I think would be really incredible for it to happen. Come back in 3 years, somebody else will be talking about the GIL being removed from Python. It won't be me. So we're finally finished talking about concurrency in Python, so let's get back to talking about Wordle, which is a lot more fun. First up, all the examples I've shared, they've been in easy mode. I personally play Wordle in hard mode. So for me to compare whether I'm doing well against a computer, it would be interesting to see what would make this solver work in hard mode. I wrote this code really, really well, as it turns out. And so it's just a matter of changing the words that you can guess from the full set of words to just a set of possible solutions. It's a very small change because I thought about the design of my code up front. It very slightly changes the guesses that it makes. It significantly reduces the time it takes to make a second and a third guess. And that's because hard mode is hard because you have to use the information that is revealed to you. There are fewer words that you're allowed to use to choose your guess. So there's fewer words to choose from. The solution space is much smaller. It takes less time to solve. sepal, by the way, are the parts of the calyx of a flower. So finally, how good is this solver at solving actual Wordle? So before the New York Times took over, the full set of answers of Wordle was visible in the JavaScript source code of the game. Very cool. You can find copies of the old version of Wordle from before the New York Times all over the internet. It's functional because all of the code was in the JavaScript source. It's hosted in so many places, you can find it, okay? I'm not going to tell you where, but it's there. There's about 2,300 words in that answer list. And we can run our solver against all of those words in the answer list. Firstly, to establish a baseline, let's just see what it's like if our guessing strategy is to randomly guess from the set of possible solutions. It solves the game in about 90% of the time. There are 3 words in there that triggered a bug. I didn't investigate this fully. I think it's just due to an answer not being available in the guessed list, and then we divide by 0 or something. The source code is online. If you can find the bug, please tell me what it is. So what about our easy mode guesser? So there's those 3 bug cases again, but it successfully solves all but one of the remaining puzzles in 6 guesses or less. It does really well. It does well more than half of those words in 4 guesses or less, which is about as well as I play. The word that it fails to solve, by the way, is joker. Basically, it takes 7 guesses by a bunch of really obscure words, including afflage, which is a type of irrigation system originating from Oman. The more you know. So we can run the same exhaustive solver in hard mode as well. It fails to solve in hard mode a lot more than in easy mode, which you've probably experienced if you play Wordle in hard mode yourself. There's a lot of cases where you get accidentally locked into a sequence of equally likely answers, where an impossible answer might have split up the options. So for this word curvy in the middle here, once you make the guess vends on the 3rd guess, if you made the guess vends instead of curdy, that would guarantee you a solution for the words curvy, kerny, or curdy, or give you a choice between curly and curry. But you can't use the word vends in hard mode because we've already ruled out S and E as possible guesses. So instead, you have to go through all the different words. And so we actually failed to solve in hard mode for about 91 cases. This time, there are 4 words that aren't on the list. I'm not really sure what's going on here. It manages to solve about 96% of cases. And there's one small optimization that you can do to the word list, which is to remove plurals. The New York Times removes words that ends in S or ES if they're plurals or transitive verbs. One thing you'll notice with my code is that it changes the opening guess from tears to pert. That is not a dirty word, I promise you. And now we solve in 97.5% of cases, but now we've got 7 words where it fails to, where it can't find any words in the guess list. That's probably because I'm removing more words than just plurals. I need to go and manually check to see what words we're ruling out here. So, recap. It is reasonably easy to write a good Wordle solver. It's a lot of fun. You should try it, or you can just copy my code and re-implement it yourself. But like, it was a lot of fun. I wrote this in an afternoon. It was great. Threads in Python, not great for Wordle-style problems, but process pools are. My sources, the YWAL word list, the original version of Wordle from which I was able to get that answer set. The New York Times has an article where they explain their algorithm for WordleBot. And there is source code, which is available on my GitHub. So thank you, everyone, for coming along. I hope you learned something. At the very least, some new 5-letter words to include in your vocabulary. Thank you.
Thank you, Christopher.
Yeah. Yeah. Okay, enjoy.
Thank you, Julia. There we go. A little better. Work. You all right? Yeah, no, but it feels like it's gonna pull off like this. Does it look stable? Looks like it. Yeah. Give me 2 minutes, if that's okay. I just want to make sure my screens are aligned. Actually, sorry, the resolution of this is different to my home setup, so and we didn't have a chance to practice this before. Oh, sorry. Okay. Sorry, just one more second. Okay. And I just need my phone out here. Give me one more minute. Okay, good to go.